Brilliant, thank you very much, and say welcome to this talk, which is a somewhat controversial title of redefining physical computing, and what does that mean? And the reason why I called it that is that physical computing is an incredibly broad term, as is project-based learning. And one thing I've been trying to do and advocating for over the last few years is sort of change people's conception about what physical computing really is. Because if you look at the academic text around what it means, it's basically using technology in any form in a classroom to further learning. And I think it's become more precise than that, and it's become more, it's got sort of coalesced around using physical computing devices such as microbit, and obviously there's many others as well, but the microbit seems to be the coming out as the de jure standard of physical computing devices, certainly in K-12 education. And so it makes sense to sort of redefine it in a way where this ecosystem of wonderful projects and resources and technologies can be seen as sort of the way to do computing in school. And the main reason for that is because lots of teachers still aren't in love with the microbit, aren't in love with physical computing, and don't see it as or at least are unaware of it as a really useful tool for teaching computing and STEM subjects more generally. So I think part of this is sort of it's a consciousness raising exercise to try and get people to think about physical computing rather than an incredibly diffuse, abstract concept, but more as a thoroughly practical, real world, engaging way of teaching. And it's a pedagogy associated with resources. And so that's really what this talk is all about. And what do we mean by that? And what are the different working parts that go into it, and the different things you need to think about wanting to consider using PBL in the computing classroom? So just to get the ball rolling, in the chat, what are your preconceptions about project-based learning and physical computing? And when I say PBL or physical computing, I'm really referring to them almost as the same thing in this sense. And it's a sense, think of it as using microbits in the computing classroom, doing projects to learn about computing, STEM, engineering, electronics, programming, all of that sort of stuff together. So it's kind of wrapping those two words and those concepts together. But please jump in the chat and just say, what are the assumed negative connotations as well as the positive ones. I mean, we've been hearing an awful lot of examples about all the positive stuff as everyone's doing, but you may have worked with colleagues that see it as a simplistic way of teaching. Is it effective? I mean, we're seeing lots of good examples of it being effective, but how do people outside of the sort of the microbit and computing bubble perceive it? And how can we seek to get over those obstacles? So, as I mentioned before, sort of the literature defines physical computing and project-based learning very, very narrow, sort of very, very broadly. Sorry, and I think we need to narrow that down a little bit. And really, sort of, it should revolve around this idea of designing and making artifacts. So, that sort of a constructivist approach, and using computers and digital technology to incorporate digital skills, and digital skills is also one of these kind of nebulous terms when you're talking about using technology, but it's about using programming things, be it in Python, make code, or whatever. But really, it's bringing those elements together, so they're designing, making, ideating, being creative, and using digital technologies to solve real problems. And it's drawing those concepts together, and that really is, certainly in my mind, what project-based learning and physical computing is all about. And you can see some examples there of some projects there that instantiate that and show that as a way of teaching and learning. And it's not just plonking an iPad in a primary school and saying that's physical computing, and that's the complete opposite end of the spectrum. I see project-based learning as being a methodology, a tool that you can use in the computing classroom, and doing it in a specific way, which is well structured, well resourced, and teachers are confident building apply it to teach computing well, and it not just being just something that you might do once every now and again, but something that you can do often. Not necessarily replace the entire curriculum, although you could. There are examples of that. The Arm School program, we have whole courses that you can replace. We've got grades from 5 through 7 and Key Stage 3 in the UK. And this is a mixture of didactic and PBL, but this is a tool that should be used as widely as possible. So let's unpack this a little bit, because one of the problems with PBL and physical computing is that it's quite complex. There's a lot of moving parts, and it's made up of a lot of different things, and you need to be confident in all of these different areas, and able to be able to deliver it effectively. And so if you're sort of weak or not confident in any of these areas, it can start to unpick it. And especially if you've got non-specialist teachers or teachers in in primary schools, or K through 5, if you're not confident in some of these areas, then it can be quite difficult and daunting to deliver as a pedagogy as well. So through the projects that are out there and through the training that's available, you can certainly become confident. And these are quite broad, but also quite shallow. You don't need to you don't need to have a master's in electronics or really understand all about semiconductors and PCBs and all that sort of stuff to be able to use project-based learning. Certainly with the microbit, and it's just understanding how these different elements come together. Certainly, you should all, I'd hope, be familiar with the microbit and what that is in terms of the hardware platform, and sort of a simple understanding about how electronics works and sort of circuits is useful, and that goes alongside things like input, process, output, and the whole idea of making. And there's all these other elements which we'll go through as part of this presentation. But that's the sort of the map, the journey of project-based learning, and how all these things fit together. And also, as you can see on the right-hand side, how the ARM School program resources, how we seek to glue those things together with a set of resources and training to try and make that as easy as possible and make that journey to delivering project-based learning in schools as simple as possible. So starting out with the hardware, I'm sure you've all seen this sort of stuff before, but it's worth reiterating some of the functionality, and certainly when you're working with colleagues who may be new to this or trying to introduce it into schools and with students as well, it's worth starting with what the features are, and this is where some of the electronics comes into it. And you don't need to go into the sort of the nitty gritty of what UART is and I2C and that sort of stuff, but it's useful to getting students to think about what the inputs are. And so things like the sensors, the accelerometer, the temperature sensor, the light sensor. And if you have older students that you're introducing this with, you can start to look at some of the more nitty gritty about how that actually works and how these physical sensors really work. And it really depends on your curriculum and what areas you're seeking to go into, but you can cover some of the more complex stuff should you wish to. And that's the beauty about project-based learning is that you can adapt the content that you're teaching in terms of depth as much as you want to, and you can do some of it didactic and you can do some of it project-based, and you can cover whole swathes of the curriculum. So getting the students to understand how this works in its can be quite simple. Obviously, there's just the buttons and the inputs and all that sort of stuff. And there's a really good video about how the new features on the V2 can expand what you can do with the microbit as well. And these new features are fantastic. I'm really excited about the V2. I was lucky enough to receive one, and it's really fun and adds a whole new world of projects that you can do with it, and opens up the opportunities to do some really interesting stuff. And this is a really good comparison. I shamelessly stole this from Johnny from a presentation he did at ARM a while ago. And it's when you're sort of explaining what a microbit is to students and getting them to understand the physical nature of a microbit, is comparing it to a smartphone, which is something that most students will at least be familiar with. There are lots of students whose only experience of technology at home may be through their parents' smartphone. And so they can understand that that has buttons, it has this touch screen, it has LEDs and and Bluetooth and comms and that sort of thing. And so thinking on those sorts of terms, it is just a device. And conceptually, a microbit is you could conceive of it as just a smaller, simpler, less powerful phone. So I think that really works in sort of translating what the hardware does. And then when you get into the sort of the programming aspect of it, I think this is the bit that can come unstuck quite quickly if you've got especially lower school teachers that aren't familiar with programming languages and things like that, and is being able to piece together the computational constructs, which can seem quite abstract and complex and terrifying to non-specialist teachers, and then saying, do the color blocks you make that simpler, and they absolutely do. And you get the purists in computer science teachers who think, no, it has to be textually derived, we have to do it in Python or C or whatever, and you have to be able to learn these computational steps in the traditional way to be able to understand it effectively, very much like how maths is taught as well. You have to be able to learn how to do subtraction, division, and be able to repeat it lots and lots of times for it to stick. But I believe certainly that you can use you can abstract away that sort of textual element of it. And you've seen examples of this in some of the other presentations during this conference, which is brilliant to see, is that using these color blocks and linking the use of those blocks to solving real world problems makes it more tangible, makes it more engaging, and they can see that these techniques that they're applying affect the real world. And I think that's really, really important for them to understand it. And there's not a lot of literature to prove this directly, although I hope there will be going forward, that teaching computational constructs in a way such as this, where you are impacting the real world and sensing real things and doing something with that data, and still applying the same sorts of techniques you would be if you were teaching it in a didactic sense, but being able to apply it confidently, and then hopefully that the intention at least is for them to be able to recall it confidently in an exam setting such as at GCSE or formal exams that they may sit as part of their time at school. And it just makes that learning journey a little bit interesting, a little bit more interesting, a little bit more engaging, a little bit easier, and hopefully it just sticks a bit longer when they come to thinking about it, when they're recalling it later. So I think that's an important thing to explore, and something to understand is that it doesn't all need to be in text, and that MakeCode is a really good environment to teach this sort of stuff. And again, obviously, this is all in MakeCode, and we in ASP have a course about that explores all of the different blocks that go into MakeCode and how they link directly to the curriculum, and how they can be explored for non-specialists. Because I think one thing that's sort of more baked in, computer science teachers will think of MakeCode or Scratch and those sorts of technologies as being too simplistic. They sort of see the color of it in the blocks and how it removes the need to indent and curly brackets and all that sort of stuff. And they think it trivializes it slightly, but arguably it doesn't. And I think you can go quite far, all the way through K-12, and teach all of the necessary constructs or computational thinking elements through these blocks. You just have to challenge them effectively and give them contexts and projects that use all of these blocks in different ways and in different combinations. And the complexity comes from combining the different blocks in complex ways, rather than just it being complex just by the nature of typing it out in a text editor. So you can actually arguably go further than what you would do in MakeCode than you would do if you were teaching them just Python in idle, arguably. But it really depends on the delivery. But you certainly shouldn't dismiss MakeCode as being too simplistic, because it really isn't. And you see lots and lots of examples of very, very simple stuff. But I'll go through today some more complex versions, and as we've seen today as well in the other presentations, there are some really, really complex stuff that you can do with this, all the way through to like data science, machine learning, and the like, which is wonderful to see and really exciting. So in terms of curriculum coverage, as we've seen again today over the course of this entire conference, is that there's lots and lots of curriculum areas that are covered by the microbit, principally sort of computer science, but it leads really into teaching math and design technology, data science, and all these different areas, and that all sort of coalesces around this concept of covering all of these different things using project-based learning. And whilst I advocate not to think of computer science or using PBL in a cross-curricular fashion, because schools tend to work in silos, and which is sad to see, but it's just a fact. Subjects tend to sort of silo away from each other, and when it's taught cross-curricular way, that can sort of lose the impetus and can lose some of the curriculum links for computing or for maths or whichever subject is kind of owning that project. And I think that's that can be complicated to navigate. So I think having a sort of computer science backbone and sort of making sure they are programming something meaningful, but leaning on things like design technology and data science and applying mathematical skills as well as tools to be able to meet the sort of the computing needs is a useful way to think about it. But it depends on your context and what sort of classroom or subject you're working with in. So that's the sort of the big picture stuff. Now let's move into some of the sorts of tools. These are the sorts of the bricks and mortar that you can use to build up the PBL model, and what's important concepts for students to understand and for you to be able to teach, for them to get how to do project-based learning effectively. And this is arguably the most important one. It's this idea of input, process, output. And it seems really simple at first, but this is an element of sort of the design thinking, and the students have to be confident in translating taking physical world inputs like the temperature or the light level, and measuring that using the sensors on the microbit, doing something with that data. This is where all the sort of the computational constructs come in, using logic, doing something with it, storing it, transmitting it, analyzing it if you're doing data science, and then having some sort of output. And it has to go through that chain for it to be a PBL project. There's no point just taking data in and storing it if you're not going to then analyze it and do something with it. And having that output could be something as simple as just having a smiley face on the screen, or it could be sending it to another microbit somewhere else, to like a gateway microbit, which then stores it in the cloud or does something different. There's a million different ways of looking at this. This is just sort of the general framework, and getting students to think about all microbit projects using this process is useful for them to be able to think systematically about computing more generally. And this is not just a way to look at microbits, it's a way to look at technology in its entirety, and get them to think about, it's not just gathering data, it's then transmitting it and how it goes through the internet and how it can go to different computers, back to servers, and then transmitted back to the microbit again, even, and going full IoT circle. And thinking about projects also in how they tackle them, and this is an important concept, and you see this in the GCSE standards as well as the CSTA standards. Is when you're thinking about projects, is having a goal. Then you have to plan and design it. So there's some like those more STEM design thinking elements. They have to be able to develop and physically make the artifact. It's not just developing it in code; it's also developing physical artifacts as well. It could be a robot, it could be a micro pet, it could be almost anything. And then testing it, that's really important. Students hate testing stuff, but it's an important part of the process. And with the physical project, it's easier to make them test it because they have to see it actually moving, and so it makes the testing fun. It's not just kind of like unit testing code where it can be quite dull and students don't really engage with it. And they're evaluating it, and they evaluate it by referring back to the original goal or the success criteria. And going through that loop lots and lots of times is really important. And this is maybe one of the weaknesses of PBL, is that students are scared of failing, and it's about building resilience in learners and getting them to fail early, fail often, and you'll go through this process many times. And in the Arm School program resources, we use the success criteria, and it kind of ramps up in complexity, so that as students go through it, they're challenged, and sometimes they have to go back and unpick previous solutions and then refactor them in a way that is more complex. And so you're kind of forcing them really to do it wrong and then do it right, or not do it wrong, but do it in one way and then think about it and doing it in another way, which stretches them a bit further, and so you can really build in that complexity, be it on the physical side or on the programming side. There's lots and lots of different ways to take it. But going through that iterative development cycle is really important. And you can see examples of this in the Arm School program resources. They're all freely available on school.arm.com. There's the microcourse book. We're just about to launch a new one of these in the new year, which involves some data science projects using the new V2 functionality, which is really exciting. I've had a lot of fun writing those, but the version 1 is on there on the website. Please do have a look at that. Also, check out the YouTube series. We've got 2 whole playlists. One of them is Introduction to Computing with Microbit, which takes you through all of the blocks in MakeCode and how to apply them in the classroom, and then another one for MicroPython, which is a huge course. There's I think 30 odd videos on there about how to do MicroPython. That's aimed at sort of GCSE or sort of grades 10 through 12 effectively, and it's how to program effectively, and they're all animated, they're all nice and fun to do. Check those out, and these are all project-based learning videos. So let's have an example of how does the Arm School program define what a PBL project actually is. And so we're going to use some of these headings which are baked into all of our resources. And so first of all, we have setting the scene, which is sort of contextualizing the problem for the learner. So something which has been designed so that students can empathize with and be at least familiar with. Now this example is used for really young students, so like primary school students, so K through grade 4, for example. And so it's something that they may be familiar with, especially with the current pandemic, for example. And so we set the scene. And as you can see with this one, they have to create an interactive pet, and the key bit there is interactive, and that's the opening up of the potential for this project. And then we have the success criteria, and this is the most important part of the ASP schema. It lays out the challenge of what they have to do, and it starts simple, and as you can see, and gets more complicated, and is open-ended towards the end as well. So as you can see, they have to make it. There's, as you can see in the top right as well up there, there is a net that we provide, and so they can cut that out and make the pets. They can color them in and all that sort of stuff. And so there's a slight challenge there. How do they get the microbit to sit inside the pet and be the face? You can see some of them have used googly eyes and sort of Velcro tape to stick it inside there. And so there's, they can be really creative, and you can do that in a lesson depending on the age range of the students. But I've seen also the students who do this with much larger pets, and they make them out of like cereal boxes and the like, and they have all sorts of things going on them and make them really creative. And you can attach motors and to make wings flap and all that sort of stuff as well. But the idea is that it has to be friendly to meet the context of the problem. Has to contain the microbit, has to have a face, which is important because then in the next bit they have to make it interact with the user. And that's where the challenge comes in, is how do you program interactions? And this is where the skill comes in, and this is where the learning happens, because students have to interpret what is an interaction. How do you play with a toy like this, and how do you sense what someone is doing with the pet, and how do you process that information? So how do you take that input, how do you process it, and then how do you have an output which makes sense to the user? So you can see that IPO model being used straight away, and it could be something as simple as it's got a smiley face by default. You pick it up, you might shake it vigorously. It doesn't like that, so you're triggering the accelerometry. It might have a threshold, let's say, of a G, and if it goes above that, it doesn't like it, and then it has a sad face. So input, process, output, and that's a very simplistic version of this, but you can go all the way through to really, really complicated ones where you've got different pets that can play rock, paper, scissors automatically. They transmit it randomly selects one of the three, it transmits it via radio, decides who wins, and then the winner celebrates, etc. And these are projects which are borne out in our micro course book. And you can see the little dog there in the middle as well. This was a really interesting project because the students, without even being taught about variables, they worked out that they could have a hunger variable, and so which would decrement over time. So they were using loops, and so it would start at 10, let's say, and go down to 0, and then it would get hungry and be sad. And then they put another microbit on the bone, which transmitted via radio on a very low power, a number, and the dog was programmed so that as the bone got close to it, it received that number, and then that incremented the hunger variable, and so it fed it. So the bone feeding the dog. Input, process, output. And so you can introduce some of the more complicated computational constructs through really fun and engaging ways. And the student did that off their own back, and they did these in groups, obviously. And but that's the kind of the discovery learning element. And whilst that wasn't intended as part of that lesson, it was just a natural consequence of the project in the context, which was really, really fun to see. So this is where we sort of advise people to start if you've never done projects before with the ASP resources, and it's a really fun one to play with. So, and here's some of the other things that we sort of structure, or the scaffolding which we provide to the learners who do this sort of project to have a go at is going through these sorts of interactions. There's lots and lots of things to play with. So back to this then. So we've covered the hardware, some of the basic electronics involved in that IPO making. We've looked at an example of project-based learning. Now, they're covering the curriculum. This is all of our resources are mapped to the CSTA curriculum and the UK one as well. They have engaging context, and they generally are solving real problems. And we have that global goals link as well as part of that. So, whilst that project isn't necessarily strictly a global goals link, all of the projects in the micro course are, and they all involve applying computational constructs and programming through MakeCode. So you can see we're already starting to get through all of these elements using some of these types of projects. So let's introduce the ARMS core program schema. Now this is the headings which I talked about before, and these are the sort of the backbone of what make up all of our resources. So the getting started, the context setting, the success criteria, and then you have pro tips, which is like the scaffolding where you can give them partial solutions, cheat sheets, and also there's the lesson content, the didactic stuff like slide decks and worksheets and that sort of stuff, which you can apply in whichever way is relevant to your learners. Older learners, you don't need as much of that. You can just give them the success criteria and the context, and they can solve it themselves. Younger learners will need a bit more structure, a bit more scaffolding. It also depends how much experience they've had with microbit and programming more generally as well. So that's down to the teacher to decide how much support they need to give. But from my perspective, we seek to give as much support that any student would need, and then the teacher can decide how much they need to apply. The stretch tasks are like additional success criteria. Essentially, they, as you can imagine, some students will get through it quicker and get through it really quickly, and so you need to be able to give them additional challenges which keep them on task, and it keeps them within that sort of subject domain, and so they just don't go off and do weird and wonderful things which students do, and you want to kind of constrain that learning onto what you want them to be focused on. And then the final thoughts is the sort of the summary. It sort of wraps up like you have learned X, Y, and Z, and it relates to the context that we were learning about in this lesson, and it gets them to reflect and think about and evaluate what they've done in that lesson. And so this is sort of the broad scheme that we apply to everything that we do in the ARMS core program, including all of our teacher CPD as well. And it's a nice box to put things in. So we've covered sort of like a more simplistic one, but what's really interesting and how the sort of the whole world of computing is evolving is going towards kind of data science, and which is really exciting to see. And this is more in the sort of the more towards the 12 end of the spectrum rather than the K, but it's sort of taking these computer science elements and some of the maths elements like statistics and using them to apply and analyze data gathered through computing and IoT, and learning something from them. So going from data to information to knowledge, and that getting to that knowledge bit is where sort of the data science comes in. It's taking that data and analyzing it in a meaningful way, and then using that to solve a particular problem. And then you can see that, well, data science can be used to do lots of interesting things. You see it applied in like banking and all the rest of it, and using machine learning models to predict people's behavior and that sort of thing. And part of the experiential learning of this is using machine learning to solve real world problems. How can machine learning can be used to solve the global goals, for example? And there's a whole world out there, and this is very, very, very new. And some of these technologies are very, very bleeding edge, but it's worth sort of opening students' eyes to the world of how data science can improve the world, not just be used to sort of capitalize from it in a business sense. I think that's an interesting concept to think about when creating new sorts of projects. And then you have the whole world of IoT, which is very emergent still, and it's electronics being baked into everything, and you can rapidly prototype IoT solutions using a microbit. And so you can we see lots of examples of that where people are making elements that take in the outside world and do something with them. And I think it's really interesting to let students know that all of this stuff that you're doing, it can be IoT, especially if it's transmitting data from their home or from their school or whatever. And this can be applied to almost anything. And again, it's that consciousness raising of that this stuff that you're learning isn't just like a fun project. This is the sort of thing that developers and partners that we work with at ARM do this as their full-time job. There's startups and businesses that do this everywhere, and they're taking this technology and applying it in the real world to solve problems for business. So there are careers in this sort of thing, and that links to that. Yes, I want to study STEM because I want to go and solve real world problems. And there are even technologies, proper IoT technologies for microbit. And it's just an example here where you can actually transmit data over IoT networks from a microbit to the cloud, so that you can analyze it, and that you can do some quite sophisticated analysis on that data. And we have examples of that in some of our teaching and learning resources available on the school website. And so this idea of engaging contexts, and I think this is incredibly important. We've seen lots of this throughout the conference as well, using the SDGs, the global goals, as a way to teach project-based learning. I think it's a fantastic set of resources, and I'll just go through an example now of one that I wrote a couple of years ago now, but it's really, really good fun. And so this is focused on goal 14. It's creating an oil spill cleaner upper, and you can get this in the micro course book. And effectively, students need to create a autonomous boat drone, and so you need some motors to power it. You need to build the boat itself. It has to float. We don't want wet microbits, and whilst it's only low voltage, it will break them if you chuck them in the paddling pool. So they have to this boat drone has to be able to drag a smart material sheet to soak up oil effectively. So that's the challenge, and it can seem quite complex. But we did this with a group of year 8 students, so grade 8 roughly, and they engaged with this really well. It's a full day project, and so this is another way of applying these projects is having like collapsed timetables where you spend a good chunk of time in delivering these projects. And so they set the scene. There's oil spills all the time. You see this in the press, and we have to create an algorithm that can you can set out a whole fleet of these autonomous boat drones, and they go out and soak this stuff up automatically. And so it has to be able to float, it has to be autonomous, and it has to be able to drag the smart material. So those are kind of the 3 key points there. And so thinking about this in terms of IPO, it has to set it off with a button press. You have to be able to program an algorithm that makes the boat go up and down over the oil spill, and it has to be able to control the servos in doing so. And that's a sort of the base level of complexity, and you can take it more complex from there in terms of dealing with ambient sea conditions. For example, how does it deal with waves? How does it avoid collision with other microbits, with other microboats? How does it deal with wind? Those sorts of things. Can you use GPS, for example? There's loads and loads of additional complexity you can bake into this should you wish to. And it's a good idea to get them to design this beforehand. This is like a sort of nice, the lesson before, for example, you get them to think about this and design it. In our resources, we provide these design thinking templates for them to start to think about the ideas beforehand. And this is why it's a good collaborative group project as well, because you can do all this. One person can be designing it, the other person then implementing it, and you go through that kind of iterative development cycle. As an example of the sorts of things that they might want to consider. Does it need to have wheels on both sides or a single thing at the back? There's loads of different ways of doing it. So why do we, why all these different elements? Why do we get them to work in groups? Why do we get them to work in this way? And this boils down to Fullen's 6 C's. Getting them to work in this way, solving tangible real world problems. It builds collaboration, because they have to collaborate to get this stuff done, because these challenges can be quite meaty. They have to be able to spend a lot of time working together. They have to think critically. They have to be able to apply sometimes novel tools like microbits and MakeCode to solve these problems. They have to be able to work out how these computational elements can be used to solve these problems. They have to do that through communication, and they also have to be creative in how they do it, not just in how they program it, but also how they build the artifact. And these things build character and citizenship, because they are solving real world global goals through the application of technology and programming and STEM skills. And so it's kind of like draws all of these different elements together in through PBL. I think that's the nice exciting bit of that. And so in summary, this is the sort of the world of PBL. It's all of these different elements all coming together to sort of shape what computing is and what physical computing and PBL can be imagined as. And so this is really kind of an open question: is this a useful way of defining physical computing and project-based learning? And if it is, then please do check out the OnSchool program resources because they're all available. If you're interested in the theory that goes behind all of this, this is a snapshot from our edX course, which is a teacher CPD available on edX.com, I think it is, or .org. And this is the learning landscape, and this shows you all of the different theories and orthodoxies that underpin this approach to project-based learning and physical computing. And it's a really complex world, and I didn't quite appreciate when I first went into this how much literature and orthodoxy there is out there surrounding project-based learning as an approach. And so if you want to learn more about the sort of the underpinning learning theory, do check that out, because it all pieces together really, really well, and we explore that through the course. It's quite a chunky course, but it's really detailed, and it's a mixture of theory, practice, assessment, and soft skills, which is quite nice to see. And that's, as I say, available online. If you're familiar with the theory already, if you're already aware of that, then maybe jump to course 2 and have a look at the practical application, where it goes through in a bit more detail the ASP approach and the other things you need to think about. And the assessment one is quite interesting, because there's PBL can be quite difficult to assess, and this goes through some sort of classic assessment theory which teachers might not be aware of. And this is learning from my time at the exam boards, and how we can use those sorts of skills to assess project-based learning. And then the last course is all about soft skills, teamwork, and the wider curriculum, and working with stakeholders, working with head teachers, organising STEM activities within schools, how to do them, how to fund them, how to organise them, that sort of stuff. It's a really, really diverse set of resources which are really useful if you want to implement physical computing or project-based learning in your classroom. So please do check that out. The courses are free. There is a paid-for certification if you need that sort of thing, but if you don't, if you just want to access the material for free, go through the audit track. So that's the way that edX define it, and then you get access to everything for free and for a given amount of time. I forget what the amount of time is, but it's you can access it. And if you do want the paid-for certification, then you can if you want to. So yes, thank you very much. Has anybody got any questions or in the chat? And if not, I will wrap it up right there. Thank you, Titus, for facilitating.